going to introduce to you Jonathan Ketchum. So what I hear about John, and I haven't met you in person, I don't believe, John, and if I have, I'm really sorry, but people say you are the sharpest tack. You are like, you know how people say not the sharpest tack in the box? You are sharper than the sharpest tack. The one thing that Jonathan and I do have in common is the Air Force. So near and dear to me. And without further ado, I will hand this over to you.
All right, thanks so much, Heather. Can you guys hear me?
You sound great.
All right, fantastic. Well, thank you, Heather, for the great introduction. As Heather mentioned, my name is John Ketchum. I'm one of the full-time threat hunters at USAA in the Cyber Threat Operations Center. And today I'd like to talk to you briefly about our project to improve the Kansa open source framework. Get the obligatory legal statement out of the way. Any opinions that I express during this presentation are my own, not my employer's, but I will say that I do work for a really awesome employer and we have a really cool mission. And part of our mission is to ensure and facilitate the financial security of our members. And one of the large ways that we do that is through innovation and through embracing of open source. And that's largely because with open source, we're able to tailor our applications to the needs of our environment. It allows us to stay on the bleeding edge of security tactics and techniques and to keep the cost low and competitive. And to my knowledge, this is one of the largest single contributions back to an open source project that USA has allowed. Over 10,000 lines of code and more on the way. So we're super excited to talk about this today. So here's a quick overview of what we'll be covering today. To be completely honest up front, there's way too much content here for me to cover in just 30 minutes. And so I'm going to be probably talking a little bit quickly and I'm going to skip some slides. I wanted to keep the slides included so that they're going to be posted after the fact on the SANS portal. And so will the videos. So if you feel like I'm going too quickly, the good news is that you can download the video later and watch it at half speed so I don't sound like a talking chipmunk. If at all possible, if you're able to save your questions for the Discord track 2 hallway that I've got, that'd be great. It'd allow me to get through more of the content with everybody. But if not, I'll try to go as quick as I can and allow a little bit of time for questions at the end. So a quick refresher, and for those of you who aren't familiar, what is Kansa? Well, let's say you've got an incident where you suspect a few hosts on your network have been compromised and you need to gather some additional forensic artifacts to support your investigation. The good news is Kansa is an excellent tool for the job. The reason is that it relies on Powershell and WinRM, which are native services in Windows. So you don't need to install any agents or do anything additional. All of the tools that you need are already there in most cases. And it allows you to run arbitrary modules. And there's a lot of community provided modules out there to collect certain artifacts. But the best part is you can write your own. So whatever it is you're looking for, you can look for exactly that by writing your own custom modules. I do want to talk about briefly what Kansa is not. It is not an endpoint detection response solution. It's not antivirus. It cannot replace your event logging solution. It's not real time. So it has a very niche place in incident response and potentially threat hunting in that you can use it to supplement those log sources to get artifacts that you're not already getting through some other means. And one of the niche areas that Kansa fills is especially in large enterprise environments where many of them are starting to feel that agent fatigue. Too many agents on the endpoints. IT is not really very positive about throwing another agent on there just for threat hunting. And the great thing about Kansa is that there's no agent required. It's relying on native Windows services and capabilities. So that's really the advantage that we have here with Kansa. There's lots of different Kansa forks out there. All of them provide great capabilities. Let's talk briefly, though, about what is a prerequisite to get Kansa to work in your environment. Well, first of all, you've got to have PowerShell. And the good news is if you're a large enterprise, you probably have PowerShell already. If you're running Windows, Windows 10 includes PowerShell v5 by default. I can tell you that for several years, we ran Kansa against the entire environment at USAA, and it works fine with Windows 7 as well, going as far back as PowerShell version 2. You're also going to need WinRM, the service WinRM, Windows Remoting, WSMan as it's otherwise known, and port 5985 or 5986 allowed through the host-based firewall. I generally recommend that you do this via a GPO or a logon script so you can achieve as wide of a reach as possible with getting those settings enabled. You're also going to need some credentials, and a lot of InfoSec professionals like to default to wanting domain admin credentials. I can tell you right now that with all of the threat hunting that we've done and the hundreds of Kansa jobs that we've run across our environment, we've never had the need for domain admin. I do recommend that whatever credentials you use, you make sure that they're part of a group that has local admin on the boxes that you're going to be running Kansa against. And in extreme cases, you may need up to the SE debug privilege, but really local admin is sufficient for any Kansa job that you're going to run. Also, Microsoft's remote server administration toolkit is super helpful. It allows you to query Active Directory through PowerShell and get a list of those target systems in Active Directory real time so that you have a list of the active machines that you want to reach out to and run Kansa against. And the next few items that I'm going to list here as prerequisites are grayed out. And that's just to denote that you only need these things to use or leverage some of the enhancements that we've added to the Kansa project in the last month or so. And the first I list here is ELK, but really any centralized logging solution will work. It just needs to be able to accept JSON formatted messages coming in on an arbitrary TCP listener port. And with our contribution back to the project, we provided a sample Grok parser for Logstash, but really, like I said, any centralized logging solution will work just fine. We also recommend deployment servers, and we'll talk more about this later, but this is what allows us to scale up and deploy Kansa jobs to hundreds of thousands of systems very, very rapidly. The exact number of servers is up to you. It really depends on the size of your environment and how quickly you want to be able to get those jobs, those Kansa jobs, out to the environment. And finally, we also recommend a staging server or set of servers, a cluster, possibly fronted by a load balancer. We use the staging server to stage auxiliary binaries or helper tools that the Kansa modules can download and use to gather additional artifacts that may not be possible with just native PowerShell. So we love Kansa and we don't want to disparage it at all. We're super excited about using it, but let's talk about its limitations. So really it's designed to be run from an analyst workstation and it's really focused on incident response. So you're kind of focused on 50 to 100 targets, maybe 1,000 if you've got a really beefy workstation and a good network connection, but it's really not designed to be run against the entire environment all at once, very rapidly. Since it's running from the analyst workstation, your real network bottleneck there is going to be deploying the job out. If you try to connect to 200,000 machines from your laptop, it's going to take a while. And then another limitation is that it's synchronous in nature, meaning that the Kansa framework connects to the endpoint and stays connected for the duration of the module that you're running, waiting for those results to come back, and then collects those results before it moves on to the next series. So serial and synchronous in nature, which are two of the problems that we're going to have to overcome to get it to scale. And finally, the results are stored on the local machine. So if you run this from your analyst workstation, your laptop, if you work in a large enterprise environment and you have more than one threat hunter, you're going to have a problem sharing those results and collaborating on them. We've done several threat hunting engagements with Kansa where we collect hundreds of millions of records, and being able to work through those hundreds of millions of records, if they're all on one person's laptop, becomes a little bit difficult. So this slide here is really just going over a visual depiction of what the serial synchronous nature of Kansa represents as far as a difficulty in scaling in the environment. I think you guys get the picture. Well, what I want to talk about is our goal. We think Kansa is great at incident response, but we wanted to use it from a threat hunting perspective. And threat hunting is all about knowing normal so that you can find those outliers. So we wanted to run one module on over 150,000 systems, get the results as quickly as possible to be able to identify those outliers in our environment. And the problem that we ran into is that it was just too slow. Even for modules that only took a couple of seconds, running that against 150,000 systems would take well over a day, and that was just not fast enough for us. Call us, Captain Impatient. So we had to come up with a solution to address that. And our first solution to address this was to throw more horsepower at the situation, right? The old Tim the Toolman Taylor solution is, let's get some more servers in there and divide up the job. Now, if you're a manager, you call this delegating the responsibility to your team. But from a computing engineer perspective, this is distributed parallelized computing. So we wrote a script that basically takes the job, and let's say you have 150,000 endpoints you want to target. It divides that task, that list of targets, up into a bunch of sub-targets, subtasks. And then it divvies them up between all of your Kansa servers. You've got in high-speed data centers with great connectivity to the rest of the environment. And the way that this works is the analyst will launch the Kansa module by calling out to the Kansa servers and invoking a regular copy of the Kansa framework on those servers to reach out to the endpoint. And each server then will reach out to its subset of targets across the environment and run that Kansa job, waiting for the job to complete, collect the results, bring them back, and then to solve that other problem, it sends all of the results into our centralized log management solution. We chose ELK for our hunting solution, but really any log solution will do. After all the results are there in ELK, you can then use ELK's dashboards, aggregations, visualizations to very quickly tease out all of those outliers and anomalies. I know many of you, your parents told you growing up that being different was good, but in a threat hunting scenario, different is suspicious and deserves an investigation. And so this is what allows us to find those outliers very, very quickly. And with this enhancement, we were able to make great success. We could run small Kansa jobs that took, maybe a minute or less in under a day. But that was still too slow for us. And that's because we needed to solve that other problem of synchronicity, the fact that Kansa by default stays connected to the endpoint while the module runs. So we needed to come up with a way to get around the synchronicity. And our solution to that was to create asynchronous Kansa jobs. We call these fire and forget modules because they're largely self-guided, autonomous modules that we can launch against an endpoint and then walk away. So the idea is that we spawn an orphan child process and have that process run the module collection and then report all of its results directly to our logging solution rather than waiting for the Kansa server. So the idea here is, in addition to our module code that's collecting the forensics we're interested in, we're also going to include some functions to standardize our results, to send them to ELK, to base64 encode and compress the entire module so we can spawn it as an orphan child process, and then include a self-unpacker functionality so that it has the ability to extract itself when it arrives on the endpoint. And we take all of that and we package it up into our fully autonomous fire and forget module that we can then deploy against the endpoint. And here's a notional view, if you speak PowerShell, of what we're doing. Really all it is taking all of that functionality, the module code to collect the artifacts, as well as everything necessary to make it autonomous, and we put it into a script block. And then we have a function that takes that script block, compresses it down, base64 encodes it, prepends the functions to decompress it and de-base64 encode it. And then we use a simple WIMI call when we land on the box to spawn an orphan child process, kind of like the Linux equivalent no-hup, so that when we disconnect from the machine, the process doesn't die. And with that, we're able to push out, just like before, using that same distributed deployment mechanism, we can push those fire and forget modules out. And we have multiple advantages here. The moment we start firing those modules out, they begin to execute in the environment. And immediately when the job is done, that system will start to report its results into ELK. So from the moment we click go, we can go into our dashboards and start the real-time analysis right away. So we have achieved success now. We're able to run Kansa jobs that take forever, and we can launch those in just a minute or two. It's fantastic. Yes, I see some questions coming in. Can you get a copy of the PowerShell blocks? Yep, the code has all been contributed back to the open source project, so it's all out there, and these slides will be made available later. But some of you in the audience probably noticed something interesting about that PowerShell block that I put up there. We look exactly like malware. If you were looking closely, looking back at that block, you'll see some key signs that should flag and throw off red alerts. We're using memory streams, we're compressing, we're base64 encoding. This looks like obfuscated PowerShell. And then you have the telltale sign of evil PowerShell at the bottom, spawning a PowerShell instance with no profile, hidden window, and obfuscated command block. That sets off all sorts of alarm bells. And you probably thought that, and so did our EDR solution and all of our monitoring. You can imagine the faces of our incident responders when hundreds and hundreds of thousands of alerts came pouring into their queue for evil PowerShell. Cybergeddon was pouring in through the gates. So we had to find a way to fix this. Our solution was fourfold. First of all, using an API, we work with our EDR to negotiate a safe word. Basically a way of dynamically suppressing the evil PowerShell that we're about to invoke by telling the EDR it's okay, it's just us. And you can make this a time-based safe word. It really depends on your EDR solution, but you're just basically doing a temporary suppression for the rule set that you have. Now, the EDR isn't the only thing that was flipping out. Our network-based detections, our Windows event logging detections were also seeing this evil PowerShell and losing their mind. So we solved that through a couple of other calls. We reach out to our password vault and get a set of temporary burner credentials. And you really only need those to be checked out for a couple of minutes, just long enough to authenticate to all 150,000 endpoints, spawn the orphan child process. And then it's okay for those credentials to temporarily expire, rotate, because you don't need them anymore. But we then use that user context for that temporary account to reach out to our source solution and say, hey, you're about to see some alerts come in. They're going to come in under the user context of X, whatever the temporary burner account was, over the duration of these times. And these are the possible alert types that you might see. Please suppress them. It's just the hunt team doing our thing. And our source solution will validate our API key that we're coming from an approved source, et cetera. And then assuming that everything passes, it'll put in a temporary suppression for any of those other alerts that aren't generated by the EDR. And finally, we reach out via Slack to the on-shift analyst to tell them what we're about to do so they don't get overwhelmed if they see any alerts that do slip through. Only at that point will we launch that Kansa Fire and Forget module, but this time it's prepended with that safe word so that the EDR will see it, but will safely ignore it as normal operations. So by now we've achieved success and we have gone to ludicrous speed. We're able to run Kansa jobs, regardless of how big the job is, we can deploy it in under a couple of minutes across the entire environment, 150,000 systems. But we have a new problem. We're tipping over services in prod. One of the things that we forgot to take into account is shared resource environments, especially your virtual desktop infrastructure or virtual server infrastructure. The way that those are allocated is they all share physical resources, and they do that with the assumption that there's no way that every single virtual machine in the environment is going to need to use its disk I/O or its RAM or its CPU all at the same time. So we'll dynamically provision it where it's needed on demand, but what are the odds that that'll happen all at once? Well, along comes our weaponized version of Kansa, which is basically a blue team botnet that's been sanctioned that tries to do all of those things all at once across every device in the environment. And we may have on a couple of occasions, bottlenecked disk I/O or spiked the CPU for every device. This is really only a problem in those shared resource environments. Fortunately, the company that I work for takes a very forward-thinking approach to these outages and looks at them as an opportunity to improve our resiliency for our provisioning of those resources. But they also don't look kindly on repeat offenders, so they expected us to make improvements so that our Kansa modules, our Fire and Forget modules, could be safely deployed in a shared resource environment. So we came up with several safeguards, the first of which is a pre-launch checklist. This one's really manual, but we check for outages beforehand using the API. And if there's already an existing outage, we're not going to launch a Kansa scan and further exacerbate problems by using more resources. But more importantly, we don't want to launch a Kansa scan if there's already an outage because we don't want to get blamed for the outage that wasn't our fault. Everybody knows you tip over the environment once or twice with Kansa, and from that moment on, every time there's an outage, somebody's calling you saying, hey, are you running a Kansa scan? So after we've checked to make sure there's not already an outage going on, we use an automated help desk notification via API, REST API call to your trouble ticketing system. And when that Fire and Forget module lands on the endpoint, it checks in and notifies the help desk saying, I'm running a Kansa job on this endpoint. If you have any questions or concerns, please reach out to the hunt team. Here's their contact info. That way, if the help desk starts to get flooded with reports of sluggishness or other problems, they can look in their help desk system and immediately see that the hunt team might be involved, and they can reach out to us to have us stop. Probably the most important safeguard that we put in is staggered execution. We can configure in a shared resource environment staggered delayed start. Basically, we give a max delay and say up to 4 hours. And when that Fire and Forget module lands on the endpoint, it chooses a random number between 0 seconds and 4 hours and goes to sleep for that random amount of time. When that time has elapsed, it wakes back up, it executes its code to collect the artifacts, sends those artifacts in, and then exits. And that's a way of wear leveling those resources that are shared across the environment. That's a huge improvement there. We also implemented a CPU limiter so we can restrict the Kansa module to just idle CPU cycles on each of the machines. And the managers will love this, but we also included performance metrics, not for them, but for us. With every Kansa Fire and Forget module, we report the number of CPU cycles used, the amount of memory, the duration that the module took to complete, and we have a dashboard, and we can see if the trend lines start to spike, we know there's a problem in the environment, and that those shared resources might be bottlenecking, and then we can do something about it. Which leads me to the next point, adding an abort function. I told you before, these were orphaned child processes, so it's not as simple as just hitting Control-C to stop it, to stop the pain from happening. So we created an abort function, which is really just another Kansa Fire and Forget module that goes out as a hunter, seeker, killer of Kansa modules and kills any running Kansa modules in the environment. And then finally, a sort of dead man switch. We set a timer to say no Kansa module for this particular type of module should run longer than X minutes. And if that time elapses and the module's still running, it'll terminate it on the endpoint without us having to do anything. So now we've got safe, fast, scalable Kansa jobs that aren't firing alerts into the queue, but we have a problem with our code management. These individual modules are getting huge because they have all of those helper functions, the autonomous functions, the alerts, the safety mechanisms, the metrics, and the module code making a change to one of those helper functions means we have to go modify every single module that we've created. So we came up with just-in-time fire and forget modules. What we did here is separate out the actual module code from all of those helper functions that are universal across all of our fire and forget modules. And we called those our fire and forget wrapper. And now the module code is very simple again. If you speak PowerShell, this is a legitimate fire and forget module. It's basically a for loop that goes through the list of all the running processes, enumerates all of the properties like the process owner, the process path, the binary name, etc., and adds them to a hash table, and then uses the add result helper function to send those into our log management solution. The problem is that the add result function that you see defined here doesn't actually exist. It's not a real function. That's one of those helpers that's defined in the wrapper. So to get around that, we created a fire and forget development template that has a bunch of stub helper functions so that you can test your code and develop it without having to have that full code base of over 700 lines of wrapper code. Here's a quick snapshot of what that stub helper function list looks like. Nothing special. But now when you invoke Kansa at launch time and you tell it you've got a fire and forget module, the Kansa framework will strip out all of that development feature and splice your module code into the wrapper dynamically, as well as transcribing any of the runtime variables that you pass through at the command line into that module. And what you have here now is a dynamically generated fire and forget module, or what we affectionately refer to as a DFIR spasm. There's a few code snippets here. I really don't have time to cover them. Like I said, all of this code is already committed to the open source Kansa repo in the main branch, so you can go download it right now, and these slides will be made available later. This is a list of all of the helper functions that are included in the wrapper, as well as all the metrics that we include in every single fire and forget job, and all of the safety mechanisms that are available every time we run a fire and forget job. And then I've got some screenshots here of a sample launch sequence. Again, not enough time to cover all of this here. I do want to point out that we ran this job here, that the Kansa module runs in under 2 seconds per endpoint, but we intentionally spaced it out over the space of an hour, showing you that delayed execution feature to show how we could take a spike of operational resource requirement and we could flatten that curve out. It seemed like a very timely reference. Finally, push bin doesn't scale. Kansa has the ability for you to push binaries out that are dependencies that your PowerShell might use. The problem is you have to push that out at launch, and that slows down your deployment. So we changed it into a pull bin and basically had the Kansa fire and forget module reach out to a web server and pull those resources down dynamically. And it can do it after it awakens from that random sleep timer. So it does wear leveling on our REST API front end as well. This is just a graphical representation of how that works. I know I'm running short on time, so I'll just skip through some of this other stuff here. These are the new command line parameters that you can use to leverage our enhancements that we've created. And some additional functions and features that we've added to the project. And one final limitation that we had to overcome is the launch command line getting too long. This is a snapshot of what an actual Kansa fire and forget launch command line looks like, because all of those safety mechanisms and everything are all dynamic, so we can configure them for each run. The problem is that's a really long command line. So there's several ways that you can solve that. We solved it here with a Kansa launcher, basically an interactive prompt that allows the hunt operator to dynamically choose their population target list, to build all the parameters, to set all the safeties, and launch or abort as necessary, as well as collecting telemetry and sending out notifications. This part has not been open sourced yet. We're working towards that. Here's some fire and forget modules that we've created. I don't have a lot of time for case studies. I wish I did. There's a whole bunch here in the slides, so I encourage you to read over them and ask me in the hallway channel in Discord. I will cover one case study, though, to give you an idea of how you can use Kansa at scale for threat hunting. So the hypothesis here is that System32 is a great place for bad guys to hide their malware, because nobody knows what's really supposed to be in there. There's a lot of binaries, and everybody's afraid of deleting anything. So it's a perfect place to hide. We have a Kansa module that will go out and enumerate the entire contents of the System32 folder and get as much metadata as possible, including file hashes, digital signatures, validating the digital signatures, etc. And then bring all of that back into our ELK stack. And from there, we can use least frequency of occurrence to pivot through to look for outliers, weird file names that aren't present everywhere, weird hashes, etc. One such output that we ran into on one hunt was that 6 machines in our environment had a copy of the utilman executable, which is supposed to be present in System32, that had a different hash than the hash present in the rest of our environment. For those of you who are veterans in the audience, you know this is a classic Windows accessibility hijack, where you can remote into the machine and hit the Windows U shortcut key, and it will pop a system shell. Now, unfortunately for us, this was not done out of malice. It was some IT administrators that were trying to regain access to a system that they had some troubles with. So the output here was really some remedial training and getting some new detections in place. But there's countless examples of this where you can use Kansa at scale to collect millions and millions of records and then be able to pivot through those to find the outliers. Unfortunately, it looks like I'm almost out of time. I might have time for a couple questions. I know that we'll be running into a break. So I'll zip through to the end. And if you have questions, please definitely hit me up in the Discord channel that I have out there, the hallway chat. I would love to talk more about this. Oh, let's go back one. All right, Heather, were there any questions that came up?
There are a few. So there's one that just came in. Are there any common threats that are highlighted when using this method?
Yeah, so that's a great question. We try to take the approach of our threat intelligence team will highlight the threats that are targeting us, and then we look at their tactics, techniques, and procedures based off of like the MITRE ATT&CK framework to see what threats that they use, what tactics and techniques they use, and we'll go out and look for those. We can write a custom Kansa module to look for those particular tactics. So a great example, there was a threat actor that leveraged the print monitor as a persistence mechanism. So we wrote a Kansa module that'll enumerate all print monitors across the environment, and then it'll find those DLLs on disk, it'll hash them, it'll enrich that by bumping those hashes up against the file reputation service, and then any of those files that the hash is unknown, we can then collect those files, run them through our malware analysis pipeline to get a disposition. So yeah, you can definitely target it to a specific threat actor or technique.
Okay, here's another one. How's running Kansa through firewalls at scale?
Yeah, that's a great question. You definitely need to have the firewall team on your side. We're fortunate that at USAA, we sit in the same room as the firewall team, and we have to have a very close partnership with them because our network is very highly segmented. And so getting Kansa capability, to reach through all of those firewalls down to the endpoint is difficult. Really, you want to restrict that as much as possible. We restricted the access for 5985 or 5986 from our hunt servers, those distributed servers that I mentioned very early on. So we really only allow that connectivity from those servers, and we only allow connectivity to those servers from our SOC subnet. So we're locking down the firewalls to only allow Kansa to be run from the Kansa servers against the environment and not the other way around.
Here's a fun one. Do you have the acronym breakdown for D for spasm?
Yeah, you can go back to that slide, but remember, it just starts off with a dynamically generated fire and forget module that has all the integrated helper functions and everything else.
All right, let's see. I think we have time for one more. Do your modules drop any data on the endpoint?
We strive to avoid making any changes to the endpoint to preserve the forensic integrity of the endpoint. So by default, we try to stay memory resident only. We're like memory resident malware, a botnet that if you reboot the computer, we're gone. But if necessary, we can drop a binary to the endpoint on the file system to leverage that binary. Great example is there's some great binaries out there from SANS mentors, SANS faculty like Registry Explorer and the RE command that allow you to quickly scrape through the Windows registry to look for large registry keys or base64 encoded registry keys. And it does it much more efficiently than PowerShell does. So yeah, we have the opportunity with that staging server to download that file temporarily. It will touch disk, run that job, and then clean up after ourselves after the fact. But most of our Kansa modules stay memory resident only and don't touch disk.
Fantastic. If you have any more questions for John, please post them in his track. He will be in the hallway, technically, I guess, all day today and tomorrow. So you can keep asking questions as they come up. Thank you for the amazing references to all the TV shows and movies from my childhood. Much appreciated. Fantastic talk. Thank you.
Thank you, Heather.